So welcome everybody. So today is the BioExcel webinar number 81, and we have what is new in GROMACS 2025. As every year when there is the GROMACS release, we have a webinar on what is new in the new GROMACS release. And today presenter that will tell us about what is in GROMACS 2025 is Berk Hess from the Royal Institute of Technology, Sweden. And I'm Alessandra hosting this webinar together with Otto and Richard. So I would like you to know that this webinar is recorded. And during this webinar, if you have any question, please use the Q&A button that you find in the application. Depends if which operating system you have. You can see this symbol or this symbol. So just press it and type your question. At the end of the presentation of Berk, we will ask you to unmute. We will unmute you so you have the chance to ask directly your question. In alternative, if you have no microphone, it will be great if you write us also together in the question. We will read the question for you. So after the webinar, if you want to ask any question, you can go to one of the BioExcel forum, in particular to the GROMACS BioExcel forum, and there is a user discussion category, and there you're most welcome to ask question if you have still a question after the webinar. Okay, something about Berk. Berk is a professor of theoretical biophysics at Royal Institute of Technology in Stockholm. He has designed algorithm for GROMACS simulation package over 2 decades. His current research focuses mainly on advanced sampling methods, aggregation of molecules, and studying wetting of surface at the molecular scale. And I can add that he's also one of the leader of the GROMACS project. So now I will give him the work to him. Just let me stop sharing. Okay, please, Berk.
Yes, thank you for the introduction. Let me share my screen. Where did my presentation disappear? There. Yes. So, welcome all to this webinar on what's new in GROMACS 2025. I just realized from the introduction that probably by this year I've been working on GROMACS for exactly 3 decades, so I should update my bio. A very long time, working more than half of my life already on this software, which we're very happy with ourselves. So I hope the users are also happy with that. So let's go through. Well, first let me. Oh, the slide is not moving. Yeah, the outline. So I'll first give a quick overview of the main features of GROMACS that are already there since, well, in 2024 and before, most of them. Then I'll go through a list of the new features in the 2025 release that came out exactly a week ago. Then a quick note on upcoming features and webinars, and then we'll have questions at the end, as Alessandra explained. Okay. So yeah, let's first explain how the release numbering is. This is always useful since many people might not know how we name our releases. So actually, I forgot to update this slide. It's actually 2025.0. We updated our naming scheme. I realized this earlier, but forgot to put the .0 there. So the 2025.0 release came out exactly a week ago, February 11th. So that's a major release, and GROMACS versions are always defined by 2 numbers. So it's year and then minor release, where the minor release in this case is .0, which should have been on this slide. So for instance, there's an example here of version 2022.5 and 2021.7. So that tells you from which major version the release is, which is often released in the year that's set there, but it could also be a late release with bug fixes, because minor releases, so the last number, they only contain bug fixes and sometimes documentation improvements. So this means that a higher minor release number is always better because you get more bug fixes. There's very seldomly new bugs introduced there because we are very conservative with changes in these minor releases. The major releases might have more changes, So some users prefer to stick with a major version for one project, which is understandable, but not necessary. I mean, results shouldn't change from one version to another. You should only get more features and usually better performance. Performance could be slightly worse in some cases, but you shouldn't get different results. But this explains our naming scheme. So the next minor release will be 2025.1 for bug fixes in the 2025.0 release. Okay. So let's first have a quick overview of what features, major features are there. So this is not new for this version, but they have been here around, although some are continuously being improved. So these are highlights which are taken from the website, www.gromacs.org. So you can look there for more information on these features. So the first one is our heterogeneous parallelization and GPU acceleration. So this is one of the things that GROMACS is well known for, is for high performance on all hardware, also on very new hardware. So for this, we collaborate with all major hardware vendors, NVIDIA, AMD, and Intel. They all have people working on GROMACS to improve performance on current and future hardware. So also this release, I'll go through some improvements in this machinery of GROMACS that makes it run very fast. Then in terms of features, there's the accelerated weight histogram method, which can enhance sampling by crossing barriers much quicker, and you get free energy landscapes. Here's an example of a 2D picture of a 2D free energy landscape, so you can get orders of magnitude faster sampling by avoiding having to wait for a long time to cross a barrier in case you have some reaction coordinate that gives you some hint in which direction to enhance the sampling. Then there's the GMX API Python interface, which is a relatively basic interface, basically replaced the command line with a Python interface. We hope in the future to have a more advanced interface that keeps things in memory in the background, but we currently don't have that yet. So this can be used to interface with all GROMACS commands using a Python interface. Then there's at the bottom row, there's the hybrid quantum classical simulations, QMMM, with an interface to CP2K, although that interface is easy to port to other packages if people are interested. So this is a very modular interface that's tested independently. So this will keep working as opposed to some older interfaces which were put together once and then you have to hope that they keep working and give correct results. So this is the interface properly tested and is very flexible for QMMM simulations, in this case with CP2K. Then there's the accelerated weight histogram method applied to alchemical transformations. So this is instead of running many independent simulations as you would do for thermodynamic integration or magnetic acceptance ratio, this method moves through lambda space dynamically. So you can in a single simulation sample all lambda states and compute the free energy profile along lambda and get the free energy difference that you're usually after. So this can trivially be parallelized by adding multiple walkers, so you can have many simulations contributing to the same result. So this is a more flexible way of parallelizing also, as opposed to having to run one simulation per lambda point. And in general, we've seen that it's either faster or it's equally fast as the standard method. So this is an advantageous method. There are tutorials on this as well for GROMACS. Then finally, there's the computational electrophysiology feature where you can apply a controlled electric field. So a popular way of applying electric field is by simply having a force acting on each charge or partial charge, but that's difficult to control the actual field in that case in a dielectric system with dielectric higher than 1. So this method here has 2 copies of the system, and then you can have 2 boundary regions with positive and negative ions, so you know exactly what field you apply, and those ions are exchanged to keep the field exactly as you want it. So there's a very controlled way of applying a field to a system. So a popular method for studying transport of ions through ion channels. So those are the major features we have. There are many more small features, but these are the features that are highlighted on the GROMACS website, which you can have a look to learn more about those. Okay, Then for new features in GROMACS 2025, so I'll go through a list of new first features and then performance improvements. So one major feature is that the Plumed package now has an interface integrated in GROMACS. This uses the AMD modules interface that is shipped with GROMACS. This interface is shipped with GROMACS and it uses the AMD modules interface that is in GROMACS that is used by multiple modules. So this is as opposed to the way it used to be, which you can still use, is where Plumed modified the GROMACS code to link into GROMACS, which is problematic for many reasons. I mean, one thing is that it's difficult to know what version of GROMACS you're exactly running or if it's modified. Then you have to hope that it's well tested because you don't know exactly what's happening inside the code. And the Plume developers might also know. So there has been, for instance, an issue which has mentioned here that if you run integration on a GPU, then the coordinates might not be up to date on the CPU. And then Plumed saw outdated coordinates, which is of course not good. So this interface, this MD modules interface guarantees that the modules that use this get up-to-date coordinates and their forces are taken into account. And this is all tested as well. So this guarantees that things keep working properly and also means that there's no more maintenance on the side of the Plumed developers to make this interface work with GROMACS since it's a fixed API or nearly fixed. So currently it's slightly feature limited, so there's no replica exchange and there's no energy as a reaction coordinate or as a bias. So this will be extended over time. So this has been built in an analogy to the Colvars interface, which actually, in that case, Colvars is completely included into GROMACS. Here, you need to still download the Plume library and link it to GROMACS, but there's no code modifications required. So this is a major advantage, both for users and for developers of Plumed and also for the GROMACS developers. So we're very happy with this development. And it's a very popular, probably the most popular plugin into GROMACS. So there's no functional improvements, but it's an improvement in how things are organized. Okay, so then a next major feature is neural network potentials. So as probably many of you are aware, I mean, there's a lot of things going on also in our field with AI, machine learning, and neural networks. So neural network potentials have been around for some time and are available in several packages. Now they're also available in GROMACS. So the idea here to quickly explain the concept is that you would like to represent some potential, some interaction, which is often complex, with a neural network to evaluate it faster. So the typical example here, it could be anything, but a typical example is where you would have very accurate interaction calculations from quantum mechanics, electronic structure calculations, such, which are many orders of magnitude slower than a classical force field, and would be too slow to use in a simulation directly to capture the interactions there with a neural network and then use that in classical MD simulations. So to do this, the idea is that you look at a small environment of each atom, which atoms are around there, and then the first thing you will usually do is to enforce angular and radial symmetry, because it doesn't matter how the environment is oriented for the interactions. So to make the job easier for the neural network, you do first some transformations, so things are rotation invariant and so. And then the results of these functions are fed into a neural network together with the potential and the forces between the atoms. So then the network learns by training, learns the interactions between the atoms. And you minimize, as usual, you minimize an error function. So you get a small error in energy, for instance, between your neural network and your original data. So of course, the quality of these results of this network depends completely on what you feed it. So you need to feed a lot of different conformations and also especially high energy bad conformations. Otherwise, if not, then the network might think that some bad conformations have low energy. Okay, so then how this is fed into GROMACS is by simply activating the neural network feature, which is here at the bottom in the red square in the MDP parameters. You turn on the NM-POT, the neural network potential. You need to provide a model file for this, which comes out of the neural network. And then there are options, so you can apply it to a subgroup of the system, or you can apply it to the whole system, where there's so-called mechanical embedding if you have a subgroup. So then you have NN-MM simulations similar to QMMM, where you treat part quantum and part classical. Here would treat part with neural network and part with classical. Yes, and then some other things might need to be passed to the network, which are given here. So it's a very few parameters. So most of the information comes through this model file, which contains all the data of the model. So how this actually goes in practice is that you usually would generate. So the current interface supports Torch or PyTorch models. So you would train a model using a PyTorch, where you of course need to get your data from some accurate representation of the system. That's not listed here. So then you get your model out with an export function of TorchScript, and that data, which was in the file given in the MDP option on the previous slide, is then fed into GROMACS, where we use the PyTorch C++ API, so libtorch. So we don't want to use Python since that's too slow, and then GROMACS will evaluate this model at every step by feeding coordinates into this model and get forces back and energies. It's simple as you saw the setup, and yeah, we have a mechanical embedding scheme if you want to do hybrid simulations. So here are some preliminary performance numbers. So the numbers depend very much on both the size of the system and the complexity of the model, and also the implementation of the model. So in the complete right column, there's the classical speed of the simulations, which you see in this case, all numbers are nanoseconds per day. So it's microseconds per day. For these very small systems, you can run them very fast. I presume that's on the GPU. Then the first columns all contain results for different neural network models. So if you look at the top line first, it is a very small system, an alanine dipeptide. You see that it's actually in the first box is actually faster, a bit more than twice as fast on CPU than on GPU, because it's very small. So that means that the overheads on the GPU are higher than the actual runtime of the kernels, which are run very fast on GPU. And then there are some. So the first column is a mixed model where you have several neural network models and you average over them. If you use a single one, it's faster, as you see in the second column, and then there are some optimized models later on, or with the 105.83, so that you can get things much faster if you optimize it. So there's a lot of gain to be had here in the neural network potential or force evaluation, which happens in Torch, so outside of GROMACS. So there's probably things can become much faster because you see that the neural network potential are orders of magnitude slower than the classical. Now, finally, in the last row, there's a water box of 663 atoms. So here you see that the GPU is much faster than the CPU. The system is now somewhat bigger, although still small. But still, it's several orders of magnitude slower than normal classical MD. So we expect those numbers to improve as the models get better and the GPUs get faster. But important to keep in mind here is that these runtimes for the neural network potentials are still orders of magnitude faster than the quantum mechanics calculations they're based on. So you still have a lot of gain. So you can run very accurate simulations. But a more typical kind of case is maybe in the second column, where you do 48 atoms neural network and then 60,000 solvent probably, or protein and solvent maybe. So a ligand in a protein, for instance, would be an example. So there, things are still significantly slower, but you could have much more accurate results. And there the cost is relatively less. So it's less than 2 orders of magnitude slower. So this provides a very flexible way of running many different models. So any model that you can run in PyTorch can be plugged into GROMACS with this. More extensions are planned on this, especially concerning the embedding scheme. So there's let's see, do I have that? No. So especially the long-range electrostatics are problematic here, because those are not captured, or you don't want to capture them either by neural network potential. You would want to compute those classically, but then you need to subtract them first while training the model. So that's still an active field of research. So we hope improvements come here soon. So in the next version of GROMACS, we can have a more accurate electrostatic scheme. Okay. Then for some smaller new features. So one thing is per amino acid CMAP. So that's a correction map for pairs of dihedral. So that's a 5-body term, which was introduced first for the charm force field in the backbone to get more accurate potentials for the backbone, thereby more accurate conformations. So that has been present in GROMACS for a long time, a decade or so, probably more. But now already since sometimes there's the Ember 19 force field, so 2019. That's already 5 or 6 years old. That requires different CMAPs for every amino acid, and which that was not supported in GROMACS. So this has now been added in this release. So in principle, the Ember 19 force field is now supported by GROMACS. But we're still working on the validation of this, so it has not been included yet in this 2025.0 release, but it's likely going to be included in a new minor release because it doesn't require new code, just addition of the force field files. So at the bottom, you can see the current validation. So there's errors for energies for tripeptides with the middle peptide is probably the beginning and end are probably alanine, and then the middle is the amino acid listed in this list here. And you see the errors are very small. So they have, what is this, in the 4th decimal after the decimal point for kilojoules per mole. So very small errors. So we are quite happy with, it looks very promising. We just need to do a bit more validation here to bring out this force field. So we're very happy with this charm force field. We would also like to include newer charm force fields, but the charm developers don't want us to include them. They want to count the download links. So unfortunately, we cannot do that. Okay, then a very different new feature is concerning mostly hydrodynamics, although it can also be used for deformations in membranes or such. So in GROMACS 2024, there was a major improvement of the deform option for shear and deformation. So useful for co-ed flows, for instance, which is also shown at the bottom, where you deform a system, you make one boundary move to the left and the other boundary to the right, and you get a flow in the system, a shear flow. But you could also have a different expansion or compression or other kind of flows here. So this feature has been improved in a major way in 2020, the 2024 release a year ago, where now we have fully correct hydrodynamics, correct forces, and everything. So this is now much more useful. But in some cases, like the picture shown here, you might not want to have a shear flow where you have a pure liquid which you deform, but you might want to have walls there for whatever reason. So you want to generate, for instance, a co-ed flow between walls, as is shown here. So there's a very thin wall, which are the yellow-orange kind of atoms and the red oxygens at the top and the bottom here. And you would like to pull on these. So that often these kind of walls are not fully realistic and don't stick together well. So you need position restraints for them, as is the case here. But then, so you can pull those. That already worked. So you don't need the deform option for that. You just give velocities to these walls or accelerations, and they move. You can generate a flow profile in the liquid. Here there's actually water and hexane. The water is the red and the white is the hexane. But you might want to do this at constant pressure, and this is difficult to control. So to be able to do this, you need to have volume scaling, pressure scaling, and that was not compatible with the position restraints because you would scale them. There in GROMACS there were options to either scale all restraint coordinates with the box or to do it with respect to a center of mass, but there was only a single one. So now we support multiple centers of mass, and thereby you can scale these walls without any internal deformation in the walls, and now you can have constant pressure. So this enables much easier setup and runs of deformations of liquids within walls with a constant pressure, which is usually what you want. So this makes GROMACS a bit more versatile for hydrodynamics type simulations. maybe also some types of biomolecular simulations where you're interested in cell walls and such. So this goes automatically if you define different groups here, but more about that is in the documentation. Okay, then we switch from features to performance improvements. So there's a few somewhat smaller things to note here. No major improvements, but by now GROMACS runs very efficiently on most hardware. So there's been a lot of effort over the past years for different backends. So we now are looking at smaller improvements here and there, although this one can be quite significant. So we improved the OpenMP parallelization of the pair search and the domain decomposition setup. So the issue here is that if you run very wide MPI ranks, or maybe a single one with a large GPU, for instance, then you have many cores operating, and then, for instance, on modern NVIDIA hardware, Grace Hopper, you have 80 CPU cores with a GPU. So if you run on 80 cores and you have some code that's serial that uses a single core, then of course that becomes a bottleneck. So we have noticed several of these because before we were running usually 4 threads, 8 threads or so, OpenMP threads. But now you have an order of magnitude more, you get a lot of bottlenecks. And particularly in the pair search and the domain decomposition setup code, which are run every domain decomposition step, this hinders performance. So this is a major improvement for cases where you run a lot of threads, which actually becomes also more common now on consumer hardware, where you might have a CPU with 16 cores or 32 cores and a big GPU. So there's a nice improvements here and the improvements are extra large with the GPU because this is time where the GPU does nothing while the pair search happens or domain decomposition. Then a second big improvement, which you could have before, but you needed to do something, is that the GPU buffer operations are enabled by default now. So this is for coordinate buffers, for instance, on the GPU. This is much faster for most systems, and there's advice, for instance, from NVIDIA or so, to set environment variables before to enable this, but we've had this for a long time and it's now deemed stable. So this actually gives a major performance improvement if you're running most things on the GPU. Because by default this is now on. So it can be slower for very small systems, but for those cases it's questionable anyhow if you should use a GPU, and that's gains are to be had there by setting up your system differently. So this is not per se a new feature, but a feature that's automatically active. So probably many users didn't know about this, so they get a nice performance improvement. Then there's a large project ongoing together with AMD. So AMD GPUs currently are targeted through our SYCL backend, which is an open source general way of running on AMD, but also Intel, and you could also run it on NVIDIA hardware, but their CUDA is faster. But AMD pushes for HIP now, which in principle can be a bit faster. So currently there's the non-bonded kernel can be run on AMD GPUs through HIP, but nothing else in the simulation yet. So there's more code in the pipeline, but it wasn't ready yet for this release. So it's somewhat faster than SYCL, but currently it's not advantageous yet because you usually would also want to run PME bonded and update on the GPU, and that cannot be done yet through HIP, but can be done through SYCL. So in a few cases where you would only offload it on bonded, this could be useful, but otherwise the benefits will come in the next release, where hopefully all the other parts can also be run using HIP. Okay, then for NVIDIA, there's a GPU-initiated Halo exchange. So this is using the NVIDIA shared memory, NVIDIA search mem interface. So this is an NVIDIA implementation of the general SHMEM interface, which provides faster communication through shared memory, potentially not using MPI. But the big gain here is that you initiate the communication from a GPU kernel instead of having to initiate an MPI call, which often also happens on the CPU. But this can now be kernel level operations. So this in principle can provide a lot of performance gain by having very low overhead plus asynchronous communication. So you can, for instance, fuse the communication into the compute kernel. So when the compute is ready, you can send off the data directly and then wait for that. Or not wait for that, I mean, run other things and then asynchronously check if the data has arrived and then start operating on it. So in principle, this can give a big performance improvement. Currently, with this version just got in before the release. So the gain is rather modest in the current state, but it can be used. So for that, you need to build with NVISMEM enabled, and you need to set an environment variable as runtime to enable this. So we expect much bigger performance improvements in the future, also as the hardware evolves, but especially as the code improves here. But this can be tried now. Yes, so that's it for major new features. There are many small ones which are listed in the release notes, which I didn't touch upon here. So then a big thanks to the whole GROMACS team. So we have many people contributing to the GROMACS code. So we have people here at our Stockholm team at KTH and also at the Compute Center PDC at KTH. Then we have, as mentioned, several people at the different hardware vendors, and we have many people over the world contributing smaller and larger things to GROMACS. So a big thanks to everyone involved here, not only contributing code, but also reviewing code and maintaining it. I mean, that's also a large effort. Okay, so now a small note on future developments in GROMACS. So yeah, already mentioned the Ember 99, the Ember 19 force field will probably be added in a minor 2025 release. As said, also there's an extension of the neural network potentials for different embedding schemes underway for probably for the next release. There will be also mentioned more Plumed features for the new interface. Then there's a big effort underway for HDF5 file formats for MD-run output, which should be both faster, but also a general format there. So we don't need to invent our own format. We just need to invent our own names for the content, which can then be directly read by programs like VMD and such that already support this. So this will replace our new own format TNG, which was proprietary. So this is we can now have the advantages of everything. So good compression in a generally in a format for which there's libraries to read. So there's no new implementation needs for different codes. Then there's the promise all the time of the scalable constant pH molecular dynamics integration. So there's code available but not integrated yet. So we hope we can integrate that for the next release, but no promises here because we're always short on people for all the work that needs to be done. And finally, reintroduction of user tabulated potentials, which we also promised for a long time, but I think I can hopefully do that if I can find the time. So we had other people involved here that never had the time for it. But it's an important feature that's asked by very many users. So we should get that back and an improved version also compared to the old implementation in a very old version of GROMACS by now. Then performance improvements. So yeah, we're working on improved communication and scaling performance. So several things planned or underway there. We need to see what we'll get into the next release, but we expect improvements. As mentioned, yeah, extended HIP backend for AMD GPUs and improved NVSMEM communication for NVIDIA GPUs. So those are the things we're currently working on that hopefully make it for the next release, or at least partially. But there's probably more things that will come into the new release from also other people contributing. Then just some notes on where to get more information if people are interested. So as already mentioned, I mean, the general and highlights, there's our GROMACS website, www.gromacs.org. For documentation, there's all kinds of different documentation at manual.gromacs.org, the reference manual, the user guide, installation guides, performance guides, and many other things, development guides also. So lots of information there, but you're probably already aware of that. Then tutorials, we have a next growing portfolio of tutorials at tutorials.gromacs.org. A new tutorial here is one on mastery partitioning and multiple time stepping. Then for HPC usage, there's nice material from a workshop at Lumi, which is available at the Zenodo link listed here. And then if you want to ask questions, and follow announcements, there's the GROMACS forum, which you're probably also aware of, gromacs.bioxcel.eu, a very popular forum where you can ask questions on usage and installation. Announcements also. Then there's a developer section of that also, where you can discuss your ideas and intentions related to GROMACS development. And there's a section for third-party tools and files if you want to exchange or looking for information for tools and files or want to share those. Then developer documentation. As said, there's the developer forum at bioxcel.gromacs.org. There's a or should it be the other round, gromacs.bioxcel.org. The bi-weekly video meeting. So look at the developer forum for this. So this is an open meeting where anyone can join to hear about what's going on, or if you have the developer questions or want to exchange ideas or ask how you can contribute. There's a Slack channel, which is not so active, but some people are there, so you can ping people there and chat. Then in general, our development happens on GitLab, so you can file issues there, follow issues. So as a user also, if you think you found a bug, but please check the forums and GitLab if it's not already been reported and fixed. And then we have, if you want to start contributing to GROMACS or work on your own stuff in GROMACS, implementing things, there's now very nice material from the workshop Learning How to Code in GROMACS, which we ran in person 2 years ago, but last year or was it this year, early, online. So there are slides available, plus lectures also. So you can see the material there, where you use a lot of information on how development in GROMACS works, how things are organized in GROMACS, and how you can contribute. Okay, then upcoming webinars, which I think Alessandro will also mention at the end. So there's or at least once concerning GROMACS, there's a CROEM structure refinement webinar scheduled for beginning of March, and then a perspective on simulating whole cells with Martini at the end of March, or towards the middle of March. And finally, I want to draw your attention to the BioXcel Summer School 2025 in Sardinia, which is run from the 8th to 13th of June on biomolecular simulations, where there's not only GROMACS, but also the other BioXcel codes, and there's several speakers. I'll also be there for the first time, so I'm looking forward to that. And that was it for my side. So now there's time for questions.
Thank you very much. Thank you very much, Berk. So now we will start with the first question. So I will try to unmute the people. Just let me go to the participant list. If the people can have a microphone so they can ask you directly the question. Let me see if the person is still online. Yes. I cannot unmute them. Okay, so I will read the question. I cannot unmute the person. So I will read the question. So in the ML-MM simulation, can one do free energy perturbation between MM and ML? Or in other words, a lambda control that gradually turn on ML?
No, that cannot be done. That's an interesting question. No. Would that be possible easily? I'm thinking now. Yeah, I suppose we could just add a lambda multiplying the MM potential and the ML. So then you still need a double topology. So that's somewhat tricky. So I think it wouldn't be too hard, but would require some work. So it depends on what the interest in that is. So you can, of course, you can do free energy calculations for ML and for MM separately and compare those. So that's possible, but you can't perturb one into the other. So I've seen the developer of this interface already run free energy calculations for both and check how the free energies compare for the different for the MM and the ML to see if they're near enough. So the answer is currently certainly no, but we could consider that.
Okay, thank you. There's something, if people are interested, to consider maybe to do the survey, the BioXcel survey, to int something. But okay, this is another story. So we have another question, simply always connected to the neural neural network potential. That is, would the neural network potential be appropriate for modeling chemical reaction? He's thinking, Marcos is thinking about enzymatic catalysis, for example.
Yes, yes. So enzymatic catalysis is exactly a very suitable application field for neural network potentials. So the neural network potentials, I mean, it depends, of course, where you get your data from. But if you model it on electronic structure calculations, then and there's bond formation and bond breaking reactions in there, then you fully capture that. So you capture anything that you have in your training data. So if your training data is QM with reactions and catalysis, then yes, you get that completely
Okay.
for free, so to say. I mean, but that's what you put into the training data, of course. So yes, this is it seems like a very promising application area of neural network potentials, enzyme catalysis. Yes.
Then we have a question on the force field Amber force field 19 SB. Will the force field be backward compatible and work with GROMACS 23 and 24?
No, it will not, since it required this CMAP terms per residue that differ, as I explained. So that's a requirement for this force field. So no.
Okay, so I just jump in question. We have another question that is Valentin that is asking, will the future of CP of a constant pH MD be compatible with the current PhD builder code?
So we're thinking of reorganizing the data once once constant PHMD is integrated into an official GROMACS version, but then we'll also adapt the pH builder. So I think it would just be a matter of writing the data to a different file than it currently is. So, but I mean, we sure need that because the pH builder is a very useful tool. Otherwise, it's very difficult to set up CPHMD simulation. So the strict answer might be no, but we'll update the tool so it works.
Okay, so then I come back. We have more neural network potential question, but I think I will try to expand a little in the question. There is a question on, can you expand on the thermostat to avoid a cancellation of the net velocity along direction of flow? How are the velocity scale along that direction? It's the first question. And the second question is, does the current deform option work similarly as having Lee's and Edward boundary conditions?
So the thermostat. So if you do the deform option, this is not a new feature that was added in 2025. The better handling there. So if you use the deform option, then the velocity in the thermostat is such that the flow profile is subtracted. So that doesn't come into the velocity. It shouldn't, right? Because you don't know what the absolute velocity is along the flow profile. This is somewhat tricky to get right, but I mean this is correctly implemented. So, but of course it assumes that you have a perfect quad flow if you're doing a quad flow. I mean that the flow, so it assumes that your atoms have a relative velocity which is exactly given by the deform matrix that you apply. Otherwise, there's no way of doing this unless you use the particle dynamics of the thermostat. So yes, I mean the net velocity along the flow direction is cancelled out, and that holds for any kind of flow if it's quad or expansion flow or so. Then does the current deform option work similarly as having Lee? So I thought always Lee-Edward boundary conditions are for the case where you do not have the option in the code of deforming the box. So that's not relevant because we have triclinic boxes. And I think if I'm not mistaken, I always have to be careful about these historical things that was for the case where your code does not support this. So then you need to adapt the. Oh no, wait a minute, that's Dols and Slob. Is this Lee Edwards? Maybe it is Lee Edwards. I would need to check to get my naming right. I get confused by the different things. Maybe it is actually. Let's see, can I quickly? check this. Yes. So I think it is Lee Edwards boundary conditions. Yes. At least if you have a shear flow. I mean, the deformation is more general. You can also have different types of flows there. But for the shear flow, yes.
Okay, thank you very much, Berk. We have a question of the SD integrator. Will as there are plans to support SD integrator on GPU? And also virtual size support, I guess. There are plans to support the virtual size on GPU.
Yes, so the SD integrator, so we have, I didn't list that in the future developments. Maybe I should have put it there. Yes, because it is quite relevant. So we have a near working version of the SD integrator on GPUs, but it's not fully complete yet. And the person working on this has left the team, but we should actually complete this. So that's the reason why I didn't put it there. But yeah, we should somehow find it shouldn't be much effort to finish it, and this will give a major gain for free energy calculations on GPUs. So yeah, we have something in the works, so hopefully we can get that in soon. That would be good. And concerning virtual sites, so there's a lot of interest from people doing drug binding free energy calculations on having virtual sites on the GPUs. Also tip4p water would also be useful, I suppose. So the main challenge there is if it should work in parallel using domain composition of multiple GPUs. But my personal opinion there is now that it's worth implementing a single GPU case, which is much, much simpler. But yeah, I don't know if we currently have someone with resources, some resource available to actually do this. It's not much work. So if we can find a time or someone to do this, then yes, but I can't promise anything. This is something nice, by the way. If someone is interested in contributing, this could be something that's is not too complicated to do. The kernels one can just copy from the CPU, but they need to be in the schedule at the right point to compute the new virtual site coordinates and distribute the forces.
Okay, thank you. So then I go back. There are some questions about the use. If so, there is a question very simple about the use of if one can run MD simulation by GROMACS using a special system. As you can see, is maybe you see the question in the anonymous attendees. The second question about the question, I don't read all the system specification. My suggestion will be that this person can post on the forum, but if you have a quick answer, Berk, you can give it. Do you see the question?
Yes, but it doesn't say anything. So GROMACS runs on nearly any hardware. So the question is how big the simulation is you want to simulate and how long you want to simulate it. So that's in general is the answer. I mean, I did simulations when I started by now 3 decades ago on computers which were then several orders of magnitude slower. So it was possible to run MD simulations then. So now you can run on any system on your laptop, you can run orders of magnitude longer. So possible certainly if it's sufficient for your needs depends completely on what you actually want to simulate, much more than on the hardware itself.
Yeah, and I think this is valid also for the second question. For the third, this MSC J430X.
Yeah, that's a nice modern machine. So I would say you can run pretty fast. So again, I mean, any machine can run GROMACS. So the question is, what do you want to run? I mean, if you're running a small solvent boxes, then a CPU is sufficient. If you need to do studies of whole cells or so, then you need a big HPC machine. So it depends more on what you want to simulate than the hardware itself.
Thank you. Then we have a question on still on hardware and benchmark from the CDAC India, and they want to run a benchmark on NVIDIA 100 and V100 and H100, Intel and AMD GPU. So they ask if there is a SPAC recipe for for SPAC, which type of flag one needed to focus on. So I think I don't know if you are familiar with.
I think there should be spec recipes for all these things, is my guess. So you wouldn't need to do anything, I would think almost. I'm not an expert on spec, I must say, but I think there should be recipes for everything by now. All of these things. These are quite standard HPC setups. So my guess is there should be for all of them. But as I'm not the expert, I don't dare to give guarantees here.
No. Okay, thank you. And then we go back to neural network potential. We have still some question there. So can be combined with free energy calculations. I mean, free energy, yes, in MDP file.
Yes, it can be combined, but you cannot change the neural network, the character of the neural network atoms, particles. So you can change if you have a combined combined neural network, a classical system, then you can change the classical part. Or you can do pool calculations or so, but you can't do alchemical changes of the machine learning part.
Okay, thank you. And then we have another question always around the same machine learning potential. Why it is possible to use machine learning potential as an external model rather than deeply embedded in GROMACS in the future to update not only the machine learning force, but the charge or other property predicted by ML? I think it's missing something.
Yes, so that, I mean, deeply embedded, I think you anyhow need to call unless we implement our own neural network evaluation, which we've been thinking of if we could use very shallow networks to make things much faster. But then it's not so much a question of deeply embedded. So we've been thinking about the charges, but it's very tricky. So people are looking at machine learning potential, also predicting the charges, but those are nearly never conserve energy. So the question is if that's something we would want in GROMACS. So if you want to change the charges, then the change in charge, I mean, that changes the potential, like the Coulomb potential of the whole system, and then the charge change or the force on the charge change should include the force of all charge in the system on that charge, and that in general is not the case if you do this with machine learning. So, for instance, in the constant pH code, this is the case, and you conserve energy, but it's extremely hard to have energy conservation in machine learning potentials. So people are looking at that, but I personally think it's very dangerous to have fluctuating charges that would not conserve energy. So that's a big problem. But if that's possible, then we would likely implement that.
Yes. So, okay, thank you. And the last of neural network potential is that can be used for ligand protein chemical reaction. That I think you already answered somehow before.
Yeah, it's roughly the same. So as long as all the atoms involved in the reaction are neural network atoms, so to say, then yes. If any of those are classical, then they're classical, so they can't react unless you have reactive force field. But yeah, so this is again a case where neural network potential could be pretty useful by selecting some protein atoms to be part of the neural network group as well as the ligand, and then you could have a reaction. Yes.
Yeah. And
again,
then
for all these cases, it's tricky because the neural network a classical interaction needs to be correct. So it's not guaranteed that the results are going to be very good. Not so much because, I mean, the reaction would be accurate, but the environment, interaction with the environment have to be careful. So this is still ongoing developments here in this field to improve the quality of the potential and interaction. So things will quickly improve over time, I think. It's a fast-moving field, but as of now, you should be a bit careful and read the literature and check things so you know what the effects are of the approximations involved.
Yes. There is another following up of question. I will take just two extra question now for the time being. Maybe we can take 3. I'm not so sure. But okay, there is another one following up the people from CDAC, and they were asking for a data set for their benchmark. And then I can say that maybe Berk, you have other suggestion. Now they are using on water TPR that I don't know what
I don't know what that is, but I think this is a question that should be answered through another channel. This is not
yeah, exactly,
the right place, so we should do it through email or the forum or something.
Yeah. Okay, but in the material on Lumi, there are some TPR file that we have used for benchmark. Yeah.
Mm-hmm. Yeah,
So that you have presented in the presentation. So the people can look for, and they are specify also which TPR file we have used for benchmark there. Yeah. So that is in the presentation. And then we have another question on tabulated potential. Will the tabulated potential get any improvement in performance when reintroduced in GROMACS?
The question is improvement with respect to what? They haven't been in there for a long time, so I mean they're going to be faster than the original code probably. But no, I hope if we re-implement this, we can also get a GPU version. That would be a nice improvement. But that I won't promise at all. So, but otherwise, I don't know. It's difficult to say if the performance will be better because the way GROMACS was structured before, it fitted nicely, and that's also the reason why they got removed and not added right away, is because their structure is somewhat incompatible with the new high performance way of computing non-bonded interaction. So we need to see how this works out. On modern hardware, it's kind of inconvenient to do all these table lookups. So on a GPU, they might work somewhat better, but even there. So I can't promise anything, but I mean, it's what you compare to, right? Currently, you either need to run a very old version of GROMACS or you need to run a different code. So maybe compared to the competing code, they're quite fast. But first, we need to have any code at all. So I'm not going to promise they're going to be in the next release, but I'll do my best.
Okay, so the last question, if you can briefly answer, because then I have just an announcement. Does the MLMM support covalent bond cutting case?
That's the same question again. So as long as the bonds are between machine learning atoms, then yes. So that's how you should set things up.
Okay, thank you very much. I see that now I just have to have a small specification. The summer school, unfortunately, this registration are already closed for the summer school. But yeah, that is so. But thank you still. So it's still we will run the summer school every year. So if you are not already registered, you can have the chance to register next year. And then could you stop sharing, Berk, that I just you already did, but I will repeat. So here is the next occasion. So we will see each other in 2 weeks, the 1st of March, with Tatiana Shujeva, that she will speak about cryo-EM structure refinement with density guide simulation in GROMACS. Density guide simulation was implemented a while ago in GROMACS, but now it was already a topic of one webinar, but Tatiana is going deeper in it. And then we will have another webinar by Elisa Fadda. And then this will be on restoring protein glycolization with GlycoShape. So yeah, I hope to see you in the next occasion. I thank you very much, Berk, for the presentation. And I wish everybody a nice day or evening, depends on which time zone you are. Thank you very much. Bye-bye.